What's up, y'all? Oh man, what a beautiful day to do some math. Am I right, people? Well, today we're going to talk about the natural base and the natural log. And so you already know what a base is. We've been talking about exponentials, and the base is the thing that's being raised to a power. You also know what a log is. A log is kind of like the inverse of an exponential function. And so there's a very special kind of exponential that uses something called the natural base. And there's a special log that goes along with that base, and it's called the natural log, and that's what we're talking about today. Okay, hey, let's consider some special irrational numbers. The most famous one, the one that you know about, is pi, I'm assuming. Pi is a special number, right? It's irrational because this decimal goes on forever, and pi roughly equals 3.14159, blah, blah, blah. It goes on forever. Well, pi was discovered by somebody. It's a real number. It exists. Okay, speaking of irrational numbers, the natural base is also an irrational number. The letter E. It's on your calculator. You might have seen E before. Well, E is a special irrational number, similar to pi. It roughly equals 2.71828. This number goes on forever. It's irrational. The decimal doesn't stop, and so we need a way to kind of like express this value. We have to round it. Anyways, that number, it's in your calculator. You could do E operations with E by just using your calculator. And so this E is the natural base. It's just a number, but so like in nature, this number is seen kind of like frequently, the way that things grow. For example, like suppose that we had, let's see. Well, suppose that we had some like delicious burger, right? This burger here, bam. And suppose we left that burger out for a while and there was like some mold that started to grow on our bread. You know what I'm talking about, right? And so this mold, it would eventually kind of like grow more and more, right? Until the whole thing is just molded and nasty. Well, the way that bacteria, well, I don't know if mold actually does it this way, but bacteria grows in such a way that it's like E raised to a certain power. And so like as time goes on, the bacteria, the mold, it increases exponentially, but it increases with a special base. That's why they call it the natural base, because this growth happens kind of like in nature a lot, you know? And so anyways, this number E, it was discovered by this dude, right? Leonard Euler. Yeah, that's actually pronounced Euler. And the reason why it's called E is because he kind of got the credit for it, right? His last name starts with an E. And so he discovered it. The way he discovered it was he supposed some function, right? He said, let this function y equal the value 1 plus 1 divided by x, all raised to the x power. And so this is an exponential, right? It's a weird one. We haven't seen one where x is also in the denominator while it's being a power as well. But anyways, E is defined as here, I'll show you, as x for this function, as x approaches infinity. So like let x get super big, right? If x is really big, this number's really small, but then this number's really high. And so when you raise the power to like higher and higher values, it tends to grow a lot, right? But because this fractional part would end up being pretty small when you add it to 1, when x approaches infinity, the value of y is going to approach E. And so he discovered it. That's how he did it. It's just a little side note for you. But anyways, we're talking about the natural base function. And here's the function. F of x equals E raised to the x power. Remember, E is a number. It's roughly 2.71828. So this is the natural base function. There is an associated natural logarithm that goes with this function. And so that natural log is the log that has the base, the natural base. So log base E of x. Well, since this is such a special log, the math dudes and lady dudes out there were like, hey, let's express this in a special way. since it's the natural log, let's call it ln. I don't know, natural log. I forgot why they actually called it ln, but ln stands for the natural log. And so like the common log, which is like, you know, just log of anything, which when you don't see a base, the base is 10, right? Well, like the common log, we don't write the base. For the natural log, we don't have to write the base. Once you see an ln, you should know that the base is e. The base is e on a log, but we just write it a special way, right? So you've got this function, the natural base function e to the x, and then you've got its inverse, the log, the natural log, ln of x. Okay, so these are the two functions we're going to talk about. Here's a little side note before we get into it. Let me refresh your memory here. Remember the definition of a log. Log base 5 of 5. This is saying 5 to what power equals 5? Well, 5 to the first power equals 5, right? Whenever you have the same input as the base, it's always going to equal 1. And so if you have log base e of e, well, what's that going to equal? That's e to the first power that equals e, right? So e to the log base e of e equals 1 as well. Which means that ln, I just replaced log base e with ln. We won't write log base e. Hey, get out of here. Hold on. We won't ever write log base e. I just need you to see that ln is log base e. So ln of e equals 1, and that's an important thing to keep in mind as we move forward. Okay, and next, well, we've talked about the natural, base and the natural log, and now the question is, well, what can we do with that? First, how do we convert between exponential form and log form? So you can go from a log to an exponential, like in this way, for example. What if you had the natural log of x equaling 58? Well, because the definition of log ln is something with base e, that means that e raised to the 58th power is going to equal x. And so to go from log form here to exponential form, we have e to the 58 equaling x. And now we've just converted it into exponential form. How about from exponential form to log form? Well, suppose we had e to the x that equals 24. I like to think of it this way. If two things equal the same thing, you could take the log of both sides. You could also take the ln of both sides, the natural log, because ln is a log, right? All the same rules apply. And so if you took the log of both sides, you'd be able to bring this x out front, you remember? And then you'd have x times the ln of e. Well, the ln of e is just 1. And so, x times 1 is just x, which means that we've taken the log of the ln of both sides, which means that x equals ln of 24. Now, if you had to evaluate these by finding a number, you could type these into your calculator easily. You just have to find this e number, raise it to the 58th power, and that's what x would equal. Same here. You have an ln number, just like you have a log, a common log button. You will have ln on your calculator somewhere, if you have a calculator that has it. But anyways, you could figure out this value by typing it into your calculator. So that was converting. Next, what about simplifying? Well, when we're simplifying these, the same properties of exponents apply, and the same properties of logs apply. Now, you know these properties, and so the same thing applies. So like, for example, if you had ln of 63 minus 2 times ln of 3, well, we can simplify this by condensing it. First, we need to bring this 2 inside the log. Remember the property, right? It says, hey, that's the same as ln of 3 squared. And so now we have 2 ln's, which means they have the same base, which means we can combine them. And when you subtract, you divide the inputs, right? And so I divided 63 by 3 squared here. 3 squared is just 9. 63 divided by 9 is just 7. Which means that this simplifies into log 7, or ln of 7, natural log of 7. If you needed to evaluate to find that value, type it into your calculator, you're good to go. You're Gucci, baby. You know what I'm talking about. Anyways, what about things with the natural base? Well, it works the exact same way. E to the fifth times e squared, same way as using the other properties of exponents. Anyway, so these have the same base, which means when you multiply them, you can add the exponents. So that's just e to the seventh. You could find the value and evaluate by using your calculator. What about solving equations? Well, first, let's start with the log equations, the natural log equations. First example, what if you have log equals log? Like this example here, I've got a bunch of ln's, a bunch of natural logs equaling a bunch of other natural logs. There's no numbers here. These are all natural logs, right? And so I can condense, I can combine all my natural logs using the properties of logs. And so when you subtract, you divide, 72 divided by 4, that's just 18. So here I have ln of 18 really, equals, what about this? Well, when you add, you multiply, so that's 6 times this input, distribute. 6 times a is 6a, 6 times negative 2 is negative 12. And so now that I have log of something equals ln, natural log of something equals natural log of something, that must mean the inputs are equal, which means that since that's 18, 18 equals this guy. And so now I just have to do good old-fashioned algebra, solve for a equals 5. Keep in mind, you still have to check for extraneous solutions because the natural log still is a log. You can't input negative values into a log. And so if you get an x value or an a value, a value here, that would, when you plug it back into any of the original functions, so if I plug a 5 into a, 5 minus 2 is positive 3. And so it's not a negative, so I'm good to go. That solution still works. It would be extraneous if when you plug that value in for your unknown, if you get a negative, no solution. It's extraneous. Throw it out. You can't have negative inputs in the natural log or any other log. What if you have this type of example, log equaling a number? And so here, like ln of x minus ln of 9 equaling 7, a number. And so you do this much the same way. Use properties of logs. That's x divided by 9 in the same input. We combine these two. And if that equals 7, well, we use the definition of a log. And this means that e, remember, e is the base of this natural log. This means that e to the 7th power equals that, equals the input. And so that means that e to the 7th equals the input. And now I just need to solve for x. Multiply both sides by 9. I get 9 times e to the 7th. Now, you can find this value by typing it into your calculator. And it roughly comes out to 9,869.70. I rounded to the nearest hundred. Anyway, so that is converting between logs and exponentials, simplifying, and also solving equations for logs. Next, we'll talk about solving exponential equations that have the natural base. Okay, and lastly, how do you solve equations, exponential equations with the natural base e? Well, here I skipped showing you this version that has, like e to the something power equals e to the something else power. Because if you have a bunch of exponentials, you can combine those the same way you know how to do these. Combine all your exponentials, since they have the same base, you can combine them, get it into one exponential equaling another, and since they have the same base, that means the exponents are equal, then you could set them equal, right? So I skipped that because I thought that you could probably figure that out from doing other problems. And so what I have is just a variety of types that have numbers. Okay, so first, how about this? 3 times e to the x power equals 21. So first, I need to isolate my exponential, right? My exponential is e to the x. I need to isolate it because I need to get x out of the exponent so I can solve for it. And to do that, I need to use the inverse of e. And so, but first, because of the order of operations, I first need to get rid of this 3. This is not isolated yet. And so I need to divide both sides by 3, which means The 3's would cancel here, and I get 7 here. Now that the exponential is isolated, I can use the inverse of the natural base, which is the natural log. I take the natural log of both sides. So the natural log of this, then I use my properties of logs to bring this x out front, this exponent here. And that means x times ln of e equals ln of 7. And so the ln of e is just 1. And so you just get x on this side, right? You'd have x times ln here. I'll write it down for you. At this stage, you would have x times ln of e. Well, the ln of e is just 1. And so you just have x times 1, which is x. That's what we have here. So x equals the ln of 7. Now you could type that into your calculator and you'll get this value. Let's round to 4 decimal places unless it says otherwise. I don't know if you can see this, but bam, there you have it. Ln of, 7. Anyways, what if we change this example just a little bit? What if we made the 3 here negative, like in this example? Let's see what happens. So we do the same thing, divide both sides by -3. Then we get a -7 here. We take the ln of both sides. Now we have a negative input into a log, and that's no good. You can't do that. Which means that this would be an extraneous solution, which means that this problem's answer, no solution. Last example. How about this guy here? Well, first we need to isolate the exponential. Add 27 to both sides. So we add 27 to this, we get 81. Now that this is isolated, we could take the ln of both sides or use both sides as an input into ln. When we do that, we can use properties of logs to bring this y minus 1 out front. You see it? And then I have ln times e. This happens every time. ln, not ln times e, ln of e. ln of e is just 1, right? So y minus 1 times 1 is just y minus 1. We have that equaling ln of 8 because we took the natural log, or 81. We took the natural log of both sides. And so y minus 1 equals ln of 81. Add 1 to both sides. Type that into your calculator. Roughly your answer, 5.3944. And here you go. This is how you would type it into your calculator. Hopefully you could see it. If not, sorry. Hey, make sure if you have any questions that you're posting your questions in the discussion that is associated to this day, which is day 3 maybe? I'll have your homework posted. Make sure you do it. Make sure you reach out if you have any questions. Make sure you ask me if you need me to show you any of the problems, okay? Adios!